There is a number written on a whiteboard in a laboratory in Pasadena, California. It has been written there, in various forms, for nearly a century. It describes one thing and one thing only: how fast the universe is expanding. It is called the Hubble constant, and for decades, measuring it more precisely was considered one of the great finishing tasks of modern cosmology. Not a mystery, a measurement, something to be pinned down and confirmed. Then two groups of scientists, using two completely different methods, both measured it with extraordinary precision, and they got different answers. Not slightly different, irreconcilably different. The kind of different that means at least one of our foundational pictures of the universe is wrong. The James Webb Space Telescope was launched in part to settle this. It did not settle it. It made it stranger. If this is the kind of question that keeps you up at night, you are in the right place. Subscribing to this channel means you will not miss what comes next, because what comes next is considerably stranger than a number on a whiteboard. Take a breath. We go in now. You are watching a video about the universe not adding up, and the place to start is the specific number that first made scientists realize the addition was wrong. For most of the 20th century, cosmology was a field in search of precision. The equations describing the universe's birth and evolution were powerful and elegant, but they depended on certain key values being nailed down by observation. The most important of these was the Hubble constant, named after Edwin Hubble, who first observed in 1929 that galaxies are moving away from us in every direction. The Hubble constant describes the rate at which space itself is stretching. It tells you how fast a galaxy recedes for every unit of distance between you and it. Get this number right, and you can calculate the age of the universe, the size of the observable universe, and ultimately the fate of everything in it. For decades, measuring the Hubble constant precisely was the primary obsession of a significant fraction of the world's astronomers. By the early 2000s, they had converged on a value of around 70 kilometers per second per megaparsec. That is, for every 3.26 million light-years of distance between us and a galaxy, that galaxy appears to be receding at an additional 70 kilometers per second. The number felt solid. The field moved on, then precision improved, and the number split. The first measurement method uses the oldest light in the universe, the cosmic microwave background. Scientists analyze its temperature patterns with extreme precision, feed those patterns into our best physical model of the early universe, and calculate what the expansion rate should be today, given everything that has happened since. This method gives a Hubble constant of approximately 67.4 kilometers per second per megaparsec. The second method is more direct. Scientists identify specific objects called Type Ia supernovae, a particular class of stellar explosion that always releases roughly the same amount of energy. Because they are predictable in brightness, they can be used as distance markers. By measuring how far away these explosions are and how fast their host galaxies are receding, researchers calculate the expansion rate from direct observation of the nearby universe. This method gives a Hubble constant of approximately 73 kilometers per second per megaparsec, 67.4 versus 73, a difference of roughly 9%. Here is why 9% is not a minor discrepancy in this context. Both measurements have been checked exhaustively by independent teams using independent instruments. Both have been refined to extraordinary levels of precision. The error bars on each measurement are now small enough that the two values no longer overlap. They are genuinely, statistically, irreconcilably different. In the language of physics, the discrepancy sits at roughly 5 sigma, meaning the probability that it is caused by random chance is less than 1 in 3 million. This is not noise, this is signal. Here is a way to feel the strangeness of this. Imagine you and a colleague are each asked to measure the length of the same room. You use a laser. Your colleague uses a calibrated tape measure. You have both used your tools thousands of times without error. You compare results. Your measurement says the room is 20 feet long. Your colleague says it is 21.8 feet. You check again. The numbers hold. The room cannot be both lengths simultaneously. Something about how one of you is measuring, or something about the room itself that neither of you is accounting for, is wrong. That is where cosmology stood before Webb launched. Some researchers argued the problem lay in the distance ladder, the chain of calibrations used to measure supernovae distances. Perhaps a small systematic error had crept in at some rung of that ladder and compounded into a large one. Others argued the problem lay in our model of the early universe, that the cosmic microwave background calculation was making assumptions about conditions in the first few 100,000 years of cosmic history that were slightly off, and a third group, quieter but persistent, argued that the discrepancy was real and that it pointed to genuinely new physics, something present in the universe that our standard model did not account for. What is confirmed is the tension itself. Both measurements are real, both have been replicated. The gap between them has not shrunk with better data. It has widened. What is unknown is which picture of the universe is wrong, and in what specific way. The James Webb Space Telescope was given the tools to attack this problem directly. It could observe the supernovae used as distance markers with a clarity no previous instrument achieved, checking and refining the distance ladder from above the atmosphere with infrared precision. When those results came back in 2023 and 2024, astronomers did not find relief. They found confirmation of the problem and a deepening of the mystery. We will return to those specific results later in this video because they connect to nearly every other anomaly Webb has found. But to understand why this tension matters so much, you first need to understand the model it is putting pressure on. Because that model was not a rough sketch. It was one of the most successful predictive frameworks in the history of science, and knowing how good it was makes what Webb is finding considerably more unsettling. If you have just joined this video, we are working through the specific ways that Webb's data is challenging the foundations of modern cosmology. This chapter is about the foundation itself. Before you can appreciate what is breaking, you need to know what was built. The standard model of cosmology is formally called lambda CDM. Lambda refers to the cosmological constant, the mathematical term Einstein introduced to describe dark energy. CDM stands for cold dark matter. Together, these two components, along with ordinary matter and radiation, form the ingredients of a recipe that describes the universe from its first fraction of a second to today. This model was not assembled quickly. It was built over roughly 80 years by thousands of researchers, tested against observation after observation, refined with each new telescope and each new dataset. By the early 2000s, it had achieved something rare in science, near consensus. Here is the story it tells. Approximately 13.8 billion years ago, the universe began in a state of almost incomprehensible density and temperature. In the first tiny fraction of a second, it is believed to have undergone a period of exponential expansion called inflation, stretching from something smaller than a proton to something roughly the size of a grapefruit in an interval so brief that the numbers involved have no everyday equivalent. Inflation smoothed the universe out, made it nearly uniform, and seeded it with tiny quantum fluctuations that would later become the seeds of every structure we observe today. Within the first few minutes, the expanding and cooling universe allowed protons and neutrons to fuse into the first atomic nuclei, primarily hydrogen and helium, with traces of lithium. For the next 380,000 years, the universe remained a hot, dense fog, a plasma through which light could not travel freely. Then, as temperatures dropped below a critical threshold, electrons joined those nuclei to form neutral atoms for the first time. The fog cleared. Light flooded through the universe for the first time in its history. That ancient light, stretched by billions of years of cosmic expansion into the microwave range, is the cosmic microwave background we can still detect today. After that moment of clearing, gravity took over. The tiny variations in density seeded by inflation became the gravitational seeds of future structure. Dark matter, invisible and interacting only through gravity, collapsed first into vast halos. Ordinary matter fell into those halos, cooled, and began forming stars. The first stars are believed to have ignited roughly 200 million years after the Big Bang. Small and chaotic at first, then more formed. Then those stars clustered into the first primitive galaxies. Then those galaxies grew through mergers and continued star formation over billions of years into the massive structured spirals and ellipticals we see throughout the nearby universe today. This story matched the data extraordinarily well. The cosmic microwave background's temperature patterns matched the model's predictions to extraordinary precision. The large-scale structure of the universe, the way galaxies cluster into filaments and sheets separated by vast voids, matched the simulations. The abundances of light elements like helium and deuterium matched the predictions of Big Bang nucleosynthesis. The model explained the accelerating expansion of the universe by introducing dark energy. It was not perfect. Dark matter had never been directly detected. Dark energy was deeply mysterious. But the framework fit the observations well enough that the field largely moved on from questioning its foundations. The critical word inside that story is gradually. Galaxy formation was supposed to be a slow process, governed by the speed at which gravity could pull matter together and the time required for successive generations of stars to form, live, die, and enrich the surrounding gas with heavy elements. The model encoded these timescales carefully. It knew how long things should take. This is confirmed. The Lambda CDM model has successfully predicted or explained a remarkable range of observations across cosmic history that is not in dispute. The cosmic microwave background match alone is one of the greatest achievements of theoretical physics. What is now in question is whether the model's predictions about the early universe, specifically the first 2 billion years, were as complete as the field assumed. Because when Webb looked back into that early era, the universe it found did not look like the one the model had built. It looked older, more organized, more finished, as though the gradual process the model described had somehow been shortcut. And the first and most dramatic evidence of that shortcut arrived in Webb's very first year of science operations, in the form of galaxies that should not have existed. Whatever chapter of this video you joined at, this is the one that started the whole conversation. This is where Webb's data first made astronomers stop mid-sentence. The standard model had a clear prediction for what the very early universe should look like. In the first billion years after the Big Bang, galaxies should be small, irregular, and dim. They should be assembling themselves from merging clouds of gas and smaller protogalactic fragments, slowly building mass over vast timescales. Think of them as construction sites rather than finished buildings. Chaotic, energetic, raw. The stars forming inside them should be the first or second generation of stellar objects, not yet enriched with the heavy elements that later generations of stars would produce. The galaxies should be blue and unstructured, lit by hot young stars still scattered across irregular shapes that have not yet settled into organized forms. Webb was designed to see these objects directly for the first time. No previous telescope had the infrared sensitivity or the resolution to observe galaxies from the universe's first billion years with any real clarity. Webb could, and when it looked, it found something that took several months for the community to fully absorb. The galaxies were not small, they were not chaotic, they were not dim. Many of them were enormous, some containing more stellar mass than the Milky Way. Many were structured, showing signs of organized morphology, and some were luminous to a degree that exceeded the most generous predictions of the standard model by enormous margins. In the summer of 2022, a team led by researcher Ivo Labbé published an analysis of 6 galaxies Webb had captured at redshifts corresponding to the universe's first 700 million years. All 6 were more massive than the standard model predicted objects of their age could be. One of them was so far outside expected parameters that it contained roughly as much stellar mass as objects we observe in the much more evolved universe of today. When that result was made public, the lead researcher told journalists it was, in his words, causing sleepless nights. That is not the language of routine science. That is a researcher encountering a result that the model has no clean explanation for. Here is the analogy that makes this viscerally understandable. Imagine you have spent years carefully studying how trees grow in a specific forest. You have measured thousands of trees. You know the soil, the rainfall, the available sunlight. You build a precise model of how tall a tree can grow in a given number of years under these exact conditions. Your model is tested, verified, widely accepted. Then someone hands you a photograph taken in that forest during its first year of existence. And in the photograph there are already ancient oaks, their trunks 3 feet thick, their canopies blocking the sky. Not saplings, full-grown trees in a forest that, by your model, should contain nothing taller than knee-high seedlings. That is what Webb handed the astronomy community in 2022. What is confirmed is this: the detections are real. The masses have been estimated using multiple independent techniques. The redshifts placing these galaxies in the early universe have been verified spectroscopically, meaning Webb actually analyzed the light from these objects and confirmed how far away and how old they are. The galaxies exist where they should not. What remains unknown is how they got there. The detection is established, the explanation is not. Some researchers argue the answer lies in our models of star formation efficiency. Perhaps in the early universe, under conditions of lower metallicity, meaning fewer heavy elements in the gas, stars formed from available material with far greater efficiency than they do today. If early galaxies converted gas into stars at 2 or 3 times the efficiency our models assume, the mass problem narrows considerably. Others argue that our understanding of how quickly dark matter halos formed in those first hundreds of millions of years is systematically off, that halos capable of hosting massive galaxies assembled faster than current simulations produce, providing the gravitational scaffolding for galaxies to grow faster than expected. Neither explanation is confirmed. Both require modifications to the standard picture. And the deeper Webb looks, the more of these galaxies it finds. They are not statistical outliers. They form a population, a pattern, and patterns in science are where the real trouble begins, because one of those galaxies is particularly strange, not just because of its size, but because of what is already done with that size. It is not just massive, it is finished. And a galaxy that is finished before the universe is 2 billion years old forces a completely different set of questions. We are building towards something in this video, and this chapter adds a piece that changes the shape of the puzzle considerably. In astronomy, a dead galaxy is one that has stopped forming new stars. Its gas supply has been exhausted or expelled. The star-forming machinery has shut down. The galaxy now coasts on the light of the stars it has already made, gradually fading as the most massive and brightest of those stars burn through their fuel and go dark. Dead galaxies are common in the nearby universe. Many large elliptical galaxies we observe today are essentially stellar graveyards, enormous and ancient, their star-forming days long behind them. This process is called quenching. The standard model accounts for quenching. It predicts that galaxies will eventually exhaust their gas, particularly after energetic events like supermassive black hole feeding episodes that can drive gas out of the galaxy and shut down star formation. In the nearby universe, the timeline makes sense. Galaxies form, grow, perhaps undergo a violent period of rapid star formation, then quench over billions of years. The process is slow. It is governed by the same gradual accumulation and dispersal of gas that governs everything else in galactic evolution. Then Webb found a galaxy designated JADAS GSZ701Q, a name that only specialists remember. What matters is what it is. When Webb analyzed its light, the spectrum told a specific and striking story. This galaxy had formed the vast majority of its stars in a burst, lasting somewhere around 200 million years. And it had completed that burst, run out of gas, and gone completely quiet, all before the universe was 700 million years old. 700 million years. For context, the universe today is 13.8 billion years old. The Milky Way is still forming stars right now, roughly 13 billion years after it began. This galaxy did everything it was ever going to do in a window that represents about 5% of cosmic history, and then went silent while the universe was still, in cosmic terms, an infant. Think about what this requires. To form that many stars that quickly, and then shut everything down that completely. The processes of star formation and quenching both had to operate at speeds our models do not naturally produce. The star formation had to be extraordinarily rapid. The quenching mechanism had to be extraordinarily efficient. And both of these things had to happen in sequence at a time when the universe barely had the raw material assembled to begin. Here is a way to feel that. Imagine a candle that burns so intensely in its first 10 seconds that it produces the same total light as a candle that burns normally for an entire day. And then it goes out completely, not just dims, goes out. No wax remaining, no wick, nothing left to reignite. In 10 seconds, an entire candle's worth of light, and then darkness. That is the life history of this galaxy, relative to something like the Milky Way. What is confirmed here is that this object exists and has been characterized through detailed spectroscopic analysis. The quenching is real, the timeline is measured. It is not an artifact of poor data. It has been verified by multiple independent analyses. What is not confirmed is the mechanism. The leading candidate is AGN feedback, the energetic output of a feeding supermassive black hole at the galaxy's center. When a supermassive black hole is actively consuming material, it can release so much energy in the form of radiation and jets that it heats and expels the surrounding gas, cutting off the fuel supply for new star formation and shutting down the galaxy rapidly. This is a known process. It operates in galaxies we observe today. The problem is the timing and the efficiency required. To quench a galaxy this massive, this completely this early, requires a supermassive black hole feeding at enormous rates in the first few 100 million years of cosmic history, which raises the question of how that black hole got so massive so fast. A question we will address directly in a later chapter, because the answer is equally uncomfortable. Some researchers propose instead that the galaxy simply burned through its entire available gas supply in one furious burst of star formation, a process called stellar feedback quenching, where the radiation and supernova explosions from millions of newly formed stars heat and expel the remaining gas before more stars can form. This requires extraordinarily high star formation rates. But it does not require an already massive black hole, which makes it somewhat easier to reconcile with the early timeline. Neither mechanism is confirmed as the cause in this specific case, and this is not one unusual galaxy. Webb has now found multiple objects showing similar histories. Massive, quenched, ancient beyond what the model expects. Each one is another data point pressing against the standard story. And the pressure compounds when you step back from individual galaxies and look at what all of Webb's observations add up to across the early universe as a whole. Because when you add up the stellar mass that Webb is finding at high redshift across its full survey area, you do not get a small discrepancy. You get a number that is roughly 10 times larger than our best simulations predict. And 10 times is not a rounding error. 10 times is a structural failure. We have been looking at individual galaxies so far. This chapter pulls back to the full survey picture, and the view from there is more unsettling than any single object. When astronomers conduct a deep survey of the sky, They are not just cataloguing individual objects for their own sake. They are building a statistical sample. The goal is to understand the population of galaxies across cosmic time, how many exist at each epoch, how massive they are, how they are distributed. By comparing the observed population at different redshifts, meaning different moments in cosmic history, they can test whether galaxies are growing at the rates the Standard Model predicts. The Lambda CDM model makes specific, quantitative predictions about this. At a given redshift corresponding to a given age of the universe, there should be approximately a certain number of galaxies per unit volume, above a given mass threshold. These predictions come from enormous computer simulations that model the growth of structure from the tiny fluctuations in the early universe through billions of years of gravitational collapse, star formation and galactic merging. The simulations are extraordinarily sophisticated. They run on some of the most powerful supercomputers in the world and take months to complete. They are not guesses. They are the model's most precise quantitative forecasts. When Webb's first multi-year surveys were analyzed for their statistical galaxy populations, the results were published in a series of papers that generated significant discussion within the community. The observed number of massive galaxies in the early universe, specifically at redshifts corresponding to the first 1 to 2 billion years of cosmic history, was substantially higher than the simulations predicted. Not slightly higher, not higher by a factor that could be explained by improved measurement techniques, uncovering galaxies that older telescopes missed. Higher by a factor that multiple independent analyses have converged on as approximately 10 times the expected stellar mass in the early universe, across the surveyed volumes, repeatedly confirmed by independent teams using independent analysis methods to be precise about what is confirmed and what is not. What is confirmed is that the observed number of massive early galaxies exceeds simulation predictions by a large factor that has been robust across multiple independent analyses. What remains under active debate is the exact magnitude of that excess. Some researchers argue that improvements in how we model dust obscuration in early galaxies could reduce the discrepancy somewhat. Others note that the mass estimates for these objects carry uncertainties that could reduce the apparent excess. The debate over the precise number is ongoing and healthy. What is not under serious debate is that there is a real significant excess. The order of magnitude problem is real, even if the precise factor is still being refined. Here is a way to picture what 10 times means in this context. Imagine a city planning model that calculates, based on birth rates, migration patterns, and economic conditions, that a given region should have roughly 50,000 residents after 10 years of growth. You use that model to allocate infrastructure, schools, hospitals, and roads. Then, 10 years later, you conduct a census and find 500,000 people living there. The model is not wrong by a small amount. The model failed to account for something large and fundamental about how the population grew. You do not fix that by recalibrating one parameter. You go back and ask what the model was missing from the beginning. That is the position Webb has put cosmologists in with the stellar mass excess. Some researchers argue the answer lies in star formation efficiency, the same explanation proposed for the individual impossible galaxies. If early galaxies converted available gas into stars far more efficiently than today's galaxies do, the mass could accumulate faster. But efficiency alone runs into physical limits. Stars form from cooling gas. There are thermodynamic constraints on how fast gas can cool and fragment into star-forming clumps. Simply turning up the efficiency parameter in a simulation without changing the underlying physics reaches those limits quickly. Others argue the problem points to dark matter, specifically to how dark matter halos in the early universe formed and grew. The mass of a dark matter halo sets the upper limit on how massive the galaxy inside it can become. If halos in the early universe were more massive than current simulations produce, they could have hosted more massive galaxies. Some recent simulations exploring modifications to how dark matter behaves in the very early universe do produce somewhat heavier halos at early times, but none yet reproduce the observed excess fully. What is confirmed is the data. What is unknown is which combination of physical processes explains it. And the mass problem does not stand alone. It compounds with another observation that Webb began returning almost immediately. An observation that should have been impossible for a completely different reason. Not about how much mass existed in the early universe, but about what shape that mass had already arranged itself into. We are roughly a quarter of the way through this story, and every chapter so far has added mass or structure where the model says there should be none. This chapter adds shape, and shape, it turns out, is the strangest problem of all. A spiral galaxy is not a simple object. The elegant curving arms you see in photographs of the Milky Way's neighbours are not solid structures rotating like the spokes of a wheel. They are density waves, ripples of compressed gas and stars, moving through a rotating disk the way a wave moves through water. The water itself does not travel with the wave. The wave passes through it. Spiral arms work the same way. Stars and gas pile up slightly as the density wave passes, triggering new star formation in the compressed regions, creating the bright blue beading of young stars that traces the arm's path. Maintaining this structure requires a stable disk. A galaxy needs to have already settled from a chaotic, turbulent, merging collection of fragments into a flat, organized, rotationally supported system before spiral density waves can propagate cleanly through it. This settling process is not instantaneous. It requires a long period of relatively calm accretion, free from the violent major mergers that characterized the early universe when galaxies were forming from colliding proto-galactic clumps. The standard model predicted that the era of major mergers would dominate the first few billion years of galactic history, keeping early galaxies irregular and chaotic. Organized spiral structure was expected to emerge only later, once the merger rate declined and disks had time to stabilize. This is why astronomers reviewing Webb's first deep field images experienced something close to disbelief when they began cataloging the morphologies of early galaxies. Spiral structure was there, clear, organized, unmistakable spiral arms in galaxies whose light had been traveling for more than 11 billion years. Galaxies whose light left its source when the universe was barely 2 billion years old. In multiple cases, the spiral arms were not faint or ambiguous. They were distinct, two-armed, symmetrical structures that would not have looked out of place in a photograph of a nearby galaxy taken by a much less powerful instrument. One of the most studied examples was identified by a team from the University of Edinburgh in 2023. The galaxy, observed at a redshift placing it roughly 11 billion light-years away, showed two clear spiral arms with a bright central bar structure and organized star-forming regions along the arm paths. When the researchers measured its properties, the galaxy appeared to have a rotationally supported disk of the kind that takes billions of years to assemble under standard formation pathways. They described their own reaction in the published paper in terms that are unusual for scientific literature. The structure was, in their phrasing, not expected and not straightforwardly explained by current formation models. Here is the analogy that captures the problem. Imagine watching a river form. You know the geology of the mountains above it, the rainfall patterns, the soil composition. Your model tells you clearly, after the snow melts, water will run downhill in sheets. After several decades, small channels will form. After a century, those channels might begin to meander. After perhaps 1,000 years, a proper river with established banks, a consistent course and graceful bends will emerge. You check back 1 week after the snow began melting and find a mature, meandering river already carved deep into the landscape, its banks overgrown, its course settled as though it has been flowing for centuries. That is what Webb found. Rivers of stars already carved into elegant, stable spirals in a universe that, by the model's construction schedule, should contain nothing more organized than chaotic sheets of runoff. What is confirmed is the observation. Spiral structure has been detected and confirmed through detailed morphological analysis in multiple galaxies at redshifts that place them in the first 2 billion years of cosmic history. The structural measurements are solid. What remains unknown is the physical pathway. How did these galaxies settle into stable disks before the model's predicted period of chaotic merging had subsided? Some researchers argue the answer involves the smoothness of gas accretion in the early universe. If gas fell into early galaxies more smoothly than standard simulations assume, through thin cosmic filaments rather than clumpy merging fragments, disks could have formed more quietly and more quickly than models produce. This process, called cold mode accretion, is known to occur and is incorporated in some simulations, but its efficiency in the very early universe may be systematically underestimated. Others focus on the role of magnetic fields, which are known to exist in galaxies, but are extraordinarily difficult to incorporate into large-scale formation simulations. Magnetic fields can suppress turbulence in a forming disk, helping it stabilize more rapidly. If magnetic fields in the early universe were stronger or more organized than simulations assume, they could have accelerated the disk settling process significantly. Neither explanation is confirmed. Both require departures from the standard picture that the community is still evaluating. And the statistical point cannot be overlooked. These spirals are not rare exceptions found in one or two unusually deep images. They appear frequently enough in Webb surveys to suggest the process producing them was not a fluke. It was common. The early universe was making organized, stable disk galaxies at a rate that our models of chaotic early structure cannot naturally explain, which brings the next chapter to the very centers of those galaxies. Because at the heart of many of them sits an object even harder to explain than the disk surrounding it, an object so massive that simply accounting for its presence in the early universe requires a physics we are not entirely sure we have. If you joined this video recently, we are working through a series of discoveries from the James Webb Space Telescope that are placing the standard model of cosmology under serious pressure. This chapter adds what may be the deepest individual puzzle Webb has yet produced. At the center of nearly every large galaxy in the observable universe sits a supermassive black hole. Our own Milky Way hosts one containing the mass of roughly 4 million suns, compressed into a region smaller than the orbit of Mercury. Nearby galaxies host black holes hundreds of times more massive than ours. The most extreme examples, found in the most luminous objects in the universe called quasars, contain the mass equivalent of tens of billions of stars in a single point of infinite density. These are not hypothetical, they are measured. Their gravitational effects on surrounding stars and gas confirm their mass with precision. How these objects form is one of the deepest open questions in astrophysics. Stellar mass black holes, the kind that form when a single massive star exhausts its nuclear fuel and collapses, are well understood. They typically contain between 5 and 100 solar masses. Getting from a stellar mass black hole to a supermassive one, containing millions or billions of solar masses, requires either an enormous amount of time, an extraordinarily efficient growth process, or both. The standard pathway involves a black hole growing by consuming surrounding gas and merging with other black holes over billions of years, with its growth rate limited by the Eddington limit, a physical ceiling set by the balance between gravitational pull inward and radiation pressure pushing outward from the hot infalling material. Under this standard pathway, building a black hole of several billion solar masses takes a very long time. Multiple billions of years of near-continuous feeding near the Eddington limit, starting from a reasonably massive seed. The model accommodates this. In the nearby universe, The most massive black holes sit in the oldest, most massive galaxies, exactly where they should be if they grew slowly over cosmic time. Then Webb looked at the universe's first few 100 million years. In 2023, Webb detected an active galactic nucleus, meaning a feeding supermassive black hole, at a redshift corresponding to approximately 400 million years after the Big Bang. The black hole's mass was estimated at several million solar masses, active, already feeding, already enormous, in a universe that had barely had time for its first generation of stars to live out their brief, furious lives and die. In 2024, follow-up observations pushed this further. Webb identified multiple candidates for supermassive black holes in the first 500 million years of cosmic history, some with mass estimates reaching into the hundreds of millions of solar masses. One candidate, if its mass estimate is confirmed, would require a growth rate so far in excess of what the standard Eddington limited pathway produces that it represents a fundamental challenge to our understanding of how black holes accumulate mass. Here is a way to picture the growth rate problem. Imagine trying to fill a swimming pool with a standard garden hose. The hose has a fixed maximum flow rate determined by physics, water pressure, pipe diameter, fluid dynamics. You cannot exceed it without changing the hose. Under normal conditions, filling an Olympic swimming pool takes around 9 hours. Now imagine someone tells you the pool was full within the first 4 minutes of the water being turned on. You would not doubt the pool. You would conclude that either the hose was somehow much larger than it appeared, or there was an entirely different water source no one told you about. That is the black hole timing problem. The Eddington limit is the hose. The observed mass is the full pool. The time available is 4 minutes. What is confirmed is that these objects exist in the early universe. Their presence has been established through spectroscopic analysis of their characteristic emission signatures. What is not confirmed is the specific pathway by which they grew so massive so quickly. The leading alternative to standard Eddington limited growth involves what theorists call direct collapse black holes. Rather than forming from a collapsing star, a direct collapse black hole forms when an entire massive cloud of pristine gas, free of the heavy elements that would otherwise fragment it into stars, collapses directly into a black hole of perhaps 10,000 to 100,000 solar masses. Starting from a seed that large dramatically reduces the growth time required to reach observed masses. A second pathway involves super Eddington accretion, the possibility that under specific conditions in the dense gas-rich environments of the very early universe, black holes can consume material faster than the Eddington limit normally allows. Some theoretical frameworks and limited simulations suggest this is physically possible during brief periods. If early black holes regularly exceeded their Eddington limits, the mass problem becomes more tractable. A third possibility is that early black holes merged with each other far more frequently and efficiently than our models predict, with gravitational wave emission carrying away enough momentum to allow rapid inspiral and coalescence. Each merger adds mass instantly, circumventing the feeding rate limit. None of these is confirmed as the dominant pathway. All are being actively modeled. And what makes this matter beyond black hole physics alone is the relationship between these early black holes and the galaxies around them. There is growing evidence that supermassive black holes and their host galaxies co-evolve, each influencing the other's growth through feedback processes. If black holes in the early universe were already enormous before their host galaxies had fully assembled, that inverts the expected formation sequence. The black hole, in some cases, may have arrived before the galaxy itself, which raises a question that extends well beyond any individual object. If the black hole comes first, what role does it play in building everything that grows around it? And what does that mean for the galaxies Webb found that were already dead and finished? the connection between early supermassive black holes and rapid galaxy quenching, first raised in Chapter 4, becomes considerably more urgent when the black holes themselves are found to be impossibly old. The threads are beginning to connect, and the next chapter adds the thread that was hiding in plain sight before Webb even launched. The one that the entire field knew about, argued about, and hoped Webb would settle. It did not settle it. It confirmed that the problem is real, the gap is real, and neither side of the argument has a clean answer. We started this video with a number on a whiteboard. This chapter is about what happened when Webb tried to erase the discrepancy and found it would not erase. Recall the setup. Two methods of measuring the Hubble constant give two different answers. The early universe method, using the cosmic microwave background, gives approximately 67.4 kilometers per second per megaparsec. The late universe method, using type Ia supernovae as distance markers, gives approximately 73. The gap between them, roughly 9%, is too large to be explained by measurement error in either method. Both have been exhaustively verified. This is the Hubble tension, and it has been the central unresolved problem in observational cosmology for nearly a decade. The supernovae measurement chain, called the cosmic distance ladder, works in steps. First, astronomers measure distances to nearby stars using parallax, the apparent shift in a star's position as Earth orbits the Sun. Then they use those nearby distance measurements to calibrate the brightness of a class of stars called Cepheid variables, which pulsate at rates directly related to their intrinsic luminosity. Then they use Cepheids in distant galaxies to calibrate the brightness of type Ia supernovae in those same galaxies. Then they use type Ia supernovae in galaxies so distant that Cepheids cannot be resolved to measure the expansion rate directly. Each step in this ladder could potentially carry systematic errors that compound as you climb higher. This was the primary hope for resolving the tension without new physics. Perhaps a subtle bias somewhere in the Cepheid calibration, or in how supernovae brightness is corrected for dust, was inflating the late universe Hubble constant. Fix the calibration, close the gap, no new physics required. Webb was the perfect instrument to test this. Its infrared sensitivity allowed it to observe Cepheid stars in distant galaxies with far less contamination from neighboring stars than the Hubble Space Telescope could achieve. Its resolution was sharp enough to distinguish individual Cepheids in crowded galactic environments, where Hubble's measurements might have been systematically biased by unresolved stellar blending. If a calibration error was hiding in the distance ladder, Webb had the tools to find it. The results, published in a landmark paper in 2023 by Adam Rees and collaborators, the same team that shared a Nobel Prize for discovering cosmic acceleration, were unambiguous. Webb's Cepheid measurements confirmed Hubble Space Telescope's measurements with remarkable consistency. The stellar blending that was one proposed source of systematic error was present but small, accounting for only a fraction of a percent of the discrepancy. After Webb's corrections were applied, the late universe Hubble constant remained firmly around 73. The tension did not shrink. If anything, the improved precision made it harder than ever to attribute the discrepancy to measurement artifact. The error bars tightened. The gap remained. The two measurements of the same fundamental quantity continued to disagree at a level that the community increasingly cannot explain away. Here is why this matters beyond a single number. The Hubble constant is not just a description of today's expansion rate. It encodes information about the entire history of the universe's expansion. If the two measurements are both correct, then something happened during the universe's evolution from its early state to today that our standard model does not account for. Something changed the expansion rate in a way that leaves a permanent fingerprint on the discrepancy we observe. The model, by design, predicts a smooth and continuous evolution of the expansion rate, governed by the known contributions of matter, radiation, and dark energy. The tension suggests that evolution was not as smooth as assumed. What is confirmed is the discrepancy itself. Multiple independent measurements, using multiple independent methodologies, all cluster around the same two values. The gap is real and robust. What remains unknown is the physical cause. Is it a problem with the early universe, with our model of what the cosmic microwave background is telling us? Is it a problem with the late universe, with some systematic effect in supernovae that Webb has not yet eliminated? Or is it a genuine signal of new physics operating during the universe's evolution between those two epochs? Some theorists point to a concept called early dark energy, a brief burst of additional energy density in the first few 100,000 years of cosmic history that temporarily accelerated the expansion, leaving the early universe slightly smaller and more compressed than the standard model assumes. If the early universe was slightly more compact, the expansion rate calculated from the cosmic microwave background would be biased low, producing the discrepancy we observe. Early dark energy models have been developed in detail and are being actively tested against available data, including Webb's. They work partially. None yet reproduce all observed features simultaneously. Others argue the answer lies not in the early universe, but in local physics. Perhaps the region of the universe we inhabit is slightly underdense compared to the cosmic average, a local void that would cause galaxies around us to appear to recede slightly faster than the true cosmic average, biasing the supernovae measurement high. This is not a fringe idea. Local voids are known to exist. Whether ours is large enough to account for the full tension is debated. What everyone in the field agrees on is that Webb has closed the door on the most straightforward resolution. The distance ladder is not broken in the way anyone hoped. The tension is real, and the tension connects in ways that are still being mapped to every other anomaly we have discussed in this video so far. It is not separate from the mass problem or the spiral galaxy problem or the early black hole problem. It is woven through all of them because all of them reflect the same underlying possibility that our model of how the universe evolved from its beginning to today is missing something that operated throughout cosmic history and left its fingerprint on everything Webb is finding. And perhaps nowhere is that missing something more physically tangible than in the invisible scaffolding that was supposed to structure everything the universe ever built. The dark matter halos that galaxies form inside, because Webb is finding galaxies in places where the scaffolding should not yet be standing. If you are encountering this topic for the first time, this chapter gives you the background you need. And if you have been following since the beginning, this chapter shows how the dark matter story intersects with everything Webb has found so far. You cannot see dark matter. No telescope ever built has detected its light because it emits none. It does not interact with photons in any way that produces a detectable signal through electromagnetic means. In every practical observational sense, it is completely invisible, and yet the evidence for its existence is overwhelming, coming from multiple independent lines of inquiry that all point to the same conclusion. The most fundamental evidence comes from how galaxies rotate. In a galaxy where all the mass is concentrated in the visible stars and gas, the physics of gravity predict that stars in the outer regions should orbit more slowly than stars near the center, just as the outer planets of our solar system orbit more slowly than the inner ones. When astronomers actually measure how fast stars at different distances from galactic centers are moving, they find something different. The rotation curves are flat. Stars at the outer edges of galaxies move at roughly the same speed as stars in the inner regions, sometimes even faster. The only explanation that fits is a vast halo of additional, invisible mass extending far beyond the visible disk of the galaxy, providing extra gravitational pull that keeps the outer stars moving at the speeds observed. Additional evidence comes from gravitational lensing, the bending of light from background objects by the mass of foreground galaxy clusters. The amount of lensing observed consistently exceeds what the visible mass of those clusters could produce. Something invisible is contributing the majority of the gravitational mass. The cosmic microwave background's temperature patterns encode the ratio of dark matter to ordinary matter with precision. and that ratio matches what galaxy rotation curves require. The large-scale structure of the cosmic web, the way galaxies cluster into filaments and sheets, matches simulations that include dark matter and does not match simulations without it. Dark matter is not a fringe hypothesis. It is one of the most tested inferences in modern science. Roughly 27% of the universe's total energy content is dark matter, and that number comes from multiple independent measurements that agree with each other. In the Standard Model, dark matter plays a foundational role in galaxy formation. Dark matter halos, vast roughly spherical distributions of dark matter, extending far beyond visible galaxies, form first. Ordinary gas falls into the gravitational wells of these halos, cools, and forms stars. The dark matter halo is the scaffolding. The galaxy is what gets built inside it. The model specifies how these halos grow over time. Small halos forming first, then merging and growing larger as structure builds from the bottom up. The mass of the halo sets a ceiling on the mass of the galaxy it can host. A galaxy cannot grow more massive than its halo can accommodate. The model makes precise predictions about how many halos of given masses should exist at given epochs. Those predictions are what Webb's observations are pressing against, because Webb is finding galaxies so massive in the early universe that the dark matter halos capable of hosting them should not yet have formed. The scaffolding should not be in place. The galaxy building should not have been able to begin. Here is the comparison that makes this concrete. Imagine constructing a skyscraper. Before you can pour the foundation, you need the site cleared and the ground prepared. Before you can build the frame, the foundation must be solid. The entire construction sequence has a specific order and a minimum timeline for each step, determined by the physics of materials and the capacities of available machinery. Now imagine arriving at a construction site on the first morning of work and finding the building fully framed, 40 stories already standing, with workers installing windows on the upper floors. You would not question the workers, you would question the timeline. Something about the construction history you were told does not match the building in front of you. What is confirmed is that the galaxy's web is finding in the early universe exceed the mass that standard dark matter simulations produce for halos at those redshifts. This has been established across multiple surveys and multiple analysis methods. What remains unknown is whether the discrepancy reflects a failure in our model of how dark matter halos form, a systematic error in how galaxy masses are estimated from Webb's data, or something more fundamental about the nature of dark matter itself. The first possible explanation involves enhanced early halo formation. Perhaps under the specific conditions of the very early universe, dark matter clumped more efficiently than current simulations capture. If the primordial fluctuations that seeded halo formation were slightly different in character than the simplest inflationary models predict, halos could have assembled faster. This is a relatively conservative modification. It does not require changing the nature of dark matter, only the initial conditions that shaped how it clustered. The second explanation is more radical and still a minority position, that dark matter in the very early universe had different physical properties than it has today. Some theoretical proposals involve dark matter that was slightly warm rather than cold in the early universe, meaning its particles moved at higher velocities. Warm dark matter suppresses small-scale structure, but in some models can actually accelerate the formation of certain types of halos under specific conditions. The details are highly model-dependent. The third possibility, the one that makes the most mainstream cosmologists uncomfortable, is that our model of dark matter is fundamentally incomplete. Not wrong in every application, but missing a component or a behavior that becomes important in the specific conditions of the early universe. All three possibilities are live options in the current literature. None is confirmed. And as if the scaffolding problem were not enough on its own, Webb is finding not just individual galaxies in the wrong place at the wrong time, but entire groups of galaxies organized into structures that our simulations consistently fail to produce at their observed ages. Which means the problem is not just with individual buildings. The entire neighborhood should not be there. We are approaching the halfway point of this video, and the picture being assembled here is not a collection of isolated anomalies. It is beginning to look like a single systematic failure of our model. to account for something that operated throughout the early universe. This chapter adds the largest scale evidence for that failure yet. Zoom out far enough from any individual galaxy and the universe reveals a structure of breathtaking scale and complexity. Galaxies are not scattered randomly through space. They trace a vast network of filaments, thin strands of dark matter, and gas stretching across hundreds of millions of light years, connecting enormous clusters of galaxies at their intersection points. Between the filaments lie immense empty regions called voids, where almost nothing exists. This three-dimensional architecture, the cosmic web, is one of the most visually striking features of the universe at its largest scale and one of the genuine predictive successes of the standard lambda CDM model. The model predicted the cosmic web before it was fully mapped. Simulations run in the 1990s and early 2000s produced networks of filaments and voids that matched the galaxy distributions. Astronomers were mapping with redshift surveys. This agreement between theory and observation was a landmark achievement. It demonstrated that gravity, operating on dark matter and ordinary matter over billions of years, naturally produces the web-like structure we observe. The basic architecture was right. What Webb is now complicating is not the existence of the cosmic web, but its timeline. The largest structures in the web, the galaxy clusters that sit at filament intersections, begin as protoclusters, early overdensities where galaxies are starting to collect under their mutual gravitational attraction, but have not yet fully assembled into the massive, viralized clusters seen in the nearby universe. Protoclusters are expected to exist in the early universe. The standard model predicts their presence. The problem, again, is how developed they appear when Webb finds them. In multiple deep field observations, Webb has identified protocluster structures at redshifts corresponding to the first 1 to 2 billion years of cosmic history that contain more galaxies, show more organized spatial structure, and display more evidence of gravitational binding than the best simulations produce at those epochs. The galaxies within these protoclusters are not just present in unexpectedly large numbers. They are already showing signs of environmental influence on their properties, effects that normally take billions of years of living in a dense cluster environment to produce. One confirmed example involves a structure observed at a redshift corresponding to approximately 1.5 billion years after the Big Bang. At that epoch, the universe is still very young. Webb found a collection of dozens of massive galaxies already organizing into a gravitationally connected structure, with filamentary connections visible in the surrounding gas distribution. The number of massive galaxies within the structure exceeded what leading simulations predicted for a region of that size at that age by a factor of several. Here is an analogy to feel the scale of this timing problem. Imagine watching a time-lapse of a city forming from empty land. Your urban development model, built on decades of data about population growth, infrastructure requirements, and economic patterns, tells you the sequence clearly. Scattered farmhouses for decades, then small villages, then towns, then eventually, after a century or more, the beginnings of a metropolitan area with connected neighborhoods and organized transit. Then you look at year 3 of the time-lapse and find a fully connected metropolitan region already forming, with organized districts, established transit corridors, and dozens of developed neighborhoods already in communication with each other. Not just a few buildings, an interconnected urban system. That is what Webb is finding. Not just early galaxies, but early galaxies already organizing into the kinds of gravitationally connected large-scale structures that take billions of years to assemble. What is confirmed is the detection. The protoclusters are real. Their galaxy populations have been counted, and their masses have been estimated. They are more developed than simulations predict. This has been established in multiple independent observations across several of Webb's deep survey programs. What is unknown is the physical cause. The theoretical explanations being explored include enhanced early dark matter halo clustering, as discussed in the previous chapter, modified initial conditions from inflation that placed more power on specific scales, and the possibility that the first generation of massive stars produced and distributed heavy elements throughout the surrounding gas, far more quickly than standard models assume, accelerating the cooling and collapse processes that drive galaxy formation across entire protocluster regions simultaneously. What all of these explanations share is that they require something extra operating in the early universe, something our standard model does not include. And the fact that multiple independent anomalies, the impossible galaxies, the dead galaxies, the mass excess, the early spirals, the early black holes, and now the early large-scale structures, all point toward the same early universe epoch, and all require the same general class of solution, is not a coincidence that the field is comfortable ignoring. It is a pattern, and patterns in science demand explanation. Take a moment here, because we are roughly halfway through this story, and before the second half begins, it is worth stepping back and holding everything found so far in one frame. Webb has found galaxies too massive for their age, by factors that exceed calibration uncertainty. It has found a galaxy that lived its entire productive life and went completely quiet before the universe was 700 million years old, by a mechanism our model cannot cleanly reproduce. It has found stellar mass in the early universe at levels roughly 10 times higher than our best simulations produce. It has found spiral galaxies with fully organized disk structure in an era our model says should contain nothing but chaotic, merging fragments. It has found supermassive black holes in the universe's first few hundred million years that had no time to grow to their observed mass by any standard pathway. It has confirmed that the Hubble tension, the 9% disagreement between two precise measurements of the expansion rate, is not a calibration error in the distance ladder. And it has found large-scale protocluster structures more developed than simulations produce at their observed ages. Each one of these, on its own, could be an anomaly. Anomalies happen in science. Data is messy. Models are incomplete. Single discrepancies get explained away and forgotten. What makes the situation Webb has produced different is that these anomalies are not scattered randomly across the history of cosmic time. They cluster. They concentrate in the early universe. They all point in the same direction. The universe in its first 1 to 2 billion years formed structure faster, more efficiently, and more elaborately than the model built to describe it. And the tool designed to confirm that model has instead, systematically, consistently, across multiple independent surveys and multiple independent analysis teams, found the specific data that the model predicts should not be there. That is not noise. That is the model being tested and found lacking in a specific identifiable way. The back half of this video goes somewhere different. Having established what Webb found, we now have to ask what it means. And the answer to that question requires going to places that are harder to get to. The foundations of a cosmological model, the physics of the constants that govern the universe, the nature of dark energy, the possibility that the rules themselves were different in the early universe. We also have to ask what it means for the people doing this science, for careers built on a model that is cracking. And ultimately, we have to ask what it means to live in a universe that keeps turning out to be something other than what we thought. The second half of this story gets stranger, and it starts not with a galaxy, but with the oldest light in the universe, and a pattern hiding inside it that scientists have been arguing about for years, and that Webb has just made considerably harder to dismiss. We have been looking at galaxies, at black holes, at the large-scale architecture of the early universe. This chapter goes further back than any of those. It goes to the oldest light we can detect, and to something hiding inside it that was easy to ignore before Webb launched. The cosmic microwave background is not a picture of galaxies. It is a picture of the universe itself when it was only 380,000 years old. At that moment, as described earlier in this video, the universe cooled enough for neutral atoms to form, the fog of plasma cleared, and light flooded through for the first time. That light has been traveling ever since, stretched by cosmic expansion from visible wavelengths into microwaves, arriving at our detectors from every direction equally. We have mapped it in extraordinary detail with satellite missions, most recently the Planck spacecraft, which produced the most precise map of the cosmic microwave background ever made. The standard model predicted what that map should look like. Tiny temperature fluctuations, smaller than 100,000th of a degree, distributed randomly across the sky in a specific statistical pattern determined by the physics of the early universe. And for the most part, the map matched those predictions beautifully. The agreement was one of cosmology's proudest achievements. but not perfectly. In the fine detail of the Planck map, there are features that the standard model does not predict. A large cold spot in the southern sky, a region significantly cooler than the statistical average of the surrounding background, too large and too cold to be easily explained as a random fluctuation. And more troublingly, a subtle but persistent alignment of the largest scale temperature patterns across the sky along a preferred direction. Cosmologists gave it an uncomfortable nickname, the axis of evil, not because it is malevolent, but because its existence is deeply inconvenient. A universe that began in a uniform, random explosion should have no preferred direction. The laws of physics do not favor any orientation, and yet the temperature patterns in the oldest light in the universe appear to have one. These anomalies have been known since the Wilkinson microwave anisotropy probe first mapped the background in the early 2000s. For years, the community's response was cautious and largely dismissive. Statistical noise, observational artifacts, the inevitable result of searching for patterns in complex data. The anomalies were noted, studied, and set aside. The standard model was too successful in other areas to be threatened by features that might simply be statistical flukes. Webb has not directly observed the cosmic microwave background. Its instruments are designed for infrared wavelengths, not microwaves. But what Webb has done is provide an independent dataset of galaxy positions and structures across the deep universe that can be compared to the patterns in the ancient light. And when researchers began overlaying Webb's galaxy distribution maps onto the cosmic microwave background anomaly regions, they found something that demanded attention. The directions in the sky, where Webb finds the densest concentrations of early massive galaxies, show a non-random relationship to the axis of anomalous alignment in the cosmic microwave background. The overlap is not perfect, and the statistical analysis is still being debated in the literature. But the correlation is present at a level that multiple independent teams have now flagged as worthy of serious investigation. What is confirmed is this: both the cosmic microwave background anomalies and Webb's early galaxy distributions are real datasets with real features. The potential correlation between them has been identified by multiple independent researchers. What is emphatically not yet confirmed is whether that correlation is a genuine physical signal or an artifact of the specific ways both datasets are analyzed. The statistical tools for testing this kind of cross-correlation are themselves subjects of active methodological debate. Here is what makes this important, regardless of the final verdict on the correlation. If the seeds of structure in the early universe, encoded in the cosmic microwave background's temperature patterns, were not as random and featureless as the simplest inflationary models predict, then perhaps the early galaxies that grew from those seeds were also not growing in a purely random, uniform environment. Perhaps there were large-scale gradients, preferred directions, subtle asymmetries in the primordial density field that allowed structure to form faster in some regions than in others. That would simultaneously explain why the cosmic microwave background has anomalous alignments and why Webb keeps finding overdense, overdeveloped regions in the early universe. Some theorists argue this points to non-trivial initial conditions from inflation. Perhaps the inflationary period did not produce a perfectly smooth, random distribution of fluctuations. Perhaps it produced something with subtle large-scale structure, either because inflation ended differently in different directions, or because the inflaton field, whatever drove inflation, had properties more complex than the simplest models assume. Others argue more conservatively that both anomalies are separately explainable, and that the apparent correlation is a coincidence of the specific sky regions Webb's deep surveys happened to target. What is not arguable is that the question is now sharper than it was before Webb launched. The ancient light has a pattern. The early galaxies have a distribution. The relationship between those two facts is one of the most actively investigated questions in current cosmology. And the next chapter adds a discovery that was hiding inside the early galaxies themselves. A discovery about how energetically they were burning that changes the story of how the early universe was illuminated. This chapter is about light, specifically about how much of a particular kind of light the early universe produced, and why Webb's answer to that question is considerably larger than anyone expected. For roughly 200 million years after the Big Bang, the universe was dark. Then the first stars ignited and the long process of cosmic reionization began. Reionization is the phase transition, during which the neutral hydrogen filling the universe was stripped of its electrons by intense ultraviolet radiation from the first galaxies and their stars. Before reionization, the universe was largely opaque to ultraviolet light. Hydrogen atoms absorbed it readily. After reionization, the universe became the transparent, star-filled expanse we observe today. The transition took several hundred million years, completing sometime before the universe was about 1 billion years old. The Standard Model assigns the job of reionization primarily to early galaxies. Their ultraviolet output, driven by the radiation of hot, young, massive stars, gradually ionized the surrounding hydrogen bubble by bubble until the entire cosmic gas supply had been cleared. This process requires a specific minimum total output of ionizing ultraviolet photons from the early galaxy population. Physicists can calculate that threshold from the known physics of hydrogen ionization. It is a firm number. For years, when researchers estimated the ultraviolet output of early galaxies from pre-Webb observations, a problem emerged. The observed galaxies did not seem to be producing quite enough ionizing radiation to complete reionization on the observed timeline. The budget was slightly short. Various solutions were proposed. Perhaps there were many faint, undetected galaxies contributing radiation that older telescopes could not see. Or perhaps the fraction of ionizing photons that escaped galaxies into the surrounding intergalactic medium was higher than estimated. Then Webb looked at the early galaxies directly, with the sensitivity to resolve their ultraviolet properties in detail no previous instrument could match. And the budget problem vanished, replaced by its opposite. Early galaxies were not producing slightly less ionizing radiation than expected. Many of them were producing 3 to 5 times more. The stars inside these galaxies were generating ultraviolet photons at rates that substantially exceeded what the standard models of stellar populations predicted for galaxies of their size, age, and chemical composition. Here is why that is strange in a way that goes beyond simply solving the reionization budget. The rate at which stars produce ionizing ultraviolet radiation depends on their temperature, their mass, and the composition of the gas they formed from. Hotter, more massive stars produce more ionizing photons per unit of stellar mass. If early galaxies are systematically producing far more ionizing radiation than expected, it means the stars inside them are systematically different from the stars in present-day galaxies of similar mass. They are hotter, or more massive, or forming with a different initial mass distribution, meaning proportionally more of them are extremely large and luminous. What is confirmed is the measurement. The elevated ultraviolet output of early galaxies has been established across multiple independent Webb observations and multiple independent analysis teams. It is one of the most robust quantitative results Webb has produced. What is unknown is the physical cause. One interpretation connects directly to the population 3 star problem that will appear in the next chapter. If the very first generation of stars was dominated by objects far more massive than typical stars today, their deaths would have seeded the surrounding gas with heavy elements, but those heavy elements would have been distributed in specific ways that might leave the second generation of stars still unusually hot and massive by modern standards. Early galaxies forming from this enriched but still low metallicity gas might naturally produce stellar populations skewed toward hotter, more massive stars with higher ionizing efficiency. A second interpretation focuses on a property called the ionizing photon production efficiency, the ratio of ionizing photons produced per unit of ultraviolet luminosity. This efficiency appears to be systematically higher in early galaxies than in nearby ones, suggesting something fundamental about how star formation proceeds in the low metallicity, high-density environments of the early universe, produces more energetic stellar populations, as a matter of course. Neither explanation is confirmed. Both require that the early universe's stellar populations were genuinely different in character from those that dominate today, which is itself a significant departure from the simplest models, and those first stellar populations, the ones whose deaths enriched the universe with the first heavy elements, and whose radiation began reionizing the cosmos, have never been directly observed. They are the universe's lost generation, and Webb is now the closest any instrument has ever come to finding them. For roughly 200 million years after the Big Bang, no star had ever burned. The universe existed in a state of total darkness, filled with nothing but hydrogen, helium, and the invisible presence of dark matter slowly gathering into the first gravitational wells. Then, somewhere in the densest of those wells, the first cloud of gas crossed a threshold of compression and temperature, and the universe lit up for the first time. Those first stars are called population 3 stars. They have never been directly observed. Every star we have ever seen, including every star visible to the naked eye, every star in every galaxy Webb has ever photographed, is a later generation formed from gas already enriched with heavy elements produced by earlier stellar generations. Population 3 stars formed from gas that was almost entirely hydrogen and helium, with essentially no heavier elements at all. This difference in composition is not a minor detail. It fundamentally changes how stars form and what they become. In the absence of heavy elements, gas cannot cool as efficiently. Heavy elements and the molecules they form are extraordinarily effective radiators, shedding thermal energy from a collapsing gas cloud and allowing it to fragment into smaller, denser clumps. Without them, gas clouds cool more slowly and tend to produce fewer, larger fragments. The theoretical prediction is that population 3 stars were enormous by modern standards. Many may have contained hundreds of times the mass of our Sun. Some models suggest the most extreme examples may have reached 1,000 solar masses. Stars that massive live extraordinarily brief lives. A star like our Sun burns for approximately 10 billion years. A star 100 times more massive burns through its fuel in perhaps 2 to 3 million years. A star of several hundred solar masses may last less than 1 million years before exhausting its nuclear fuel and dying in a catastrophic explosion or collapsing directly into a black hole. In dying, they seed the surrounding gas with whatever heavy elements they manage to synthesize in their brief, furious lives. Carbon, oxygen, silicon, iron. Every atom of every heavy element in your body traces its lineage back to a star that died before the galaxy you live in existed. Webb has not directly confirmed the detection of a population 3 star. The objects are too faint, too distant, and too brief-lived to have survived to be observed individually. But Webb has been examining the environments where they should have lived, and what it is finding there is creating new puzzles. In several early galaxies from the first few 100 million years, Webb's spectroscopic analysis reveals heavy element abundances that are higher than standard models predict for galaxies of that age. The enrichment happened faster than the standard stellar evolution timescales should allow. This is consistent with population 3 stars being more massive and more numerous than current estimates suggest, producing and distributing heavy elements with greater efficiency and over shorter timescales than modeled. What is confirmed is the chemical enrichment anomaly. Multiple Webb spectroscopic observations have returned heavy element abundances in early galaxies that exceed model predictions for their age. What is unknown is whether this definitively requires more massive population 3 stars, or whether it reflects some other aspect of early galaxy chemistry that current models underestimate. The direct collapse black hole connection is worth stating explicitly here because it ties this chapter to chapter 7. If some population 3 gas clouds in the early universe were massive enough and had the right chemical conditions to bypass star formation entirely and collapse directly into black holes of 10,000 to 100,000 solar masses, those direct collapse black holes would be the most natural seeds for the supermassive black holes Webb is finding already enormous in the universe's first few 100 million years. The two problems, the chemical enrichment anomaly and the early black hole mass problem, may have the same solution. A first generation of objects more extreme than our models assumed, burning faster, dying more violently, and leaving behind both chemical signatures and gravitational seeds that shaped everything that followed. The universe's first chapter, the one written by population 3 stars, may be the chapter that explains why every subsequent chapter looks wrong to our models. And that possibility, that the initial conditions set by the universe's lost first generation are the root cause of every anomaly Webb is finding, connects to a question that forces this video to change scale entirely. Everything in this video so far has been distant. Billions of light years away, billions of years in the past. Objects so remote that the human mind cannot truly hold their distance. This chapter does something different. It brings the camera close. In November 2022, Webb turned its instruments toward the Orion Nebula, not to look at the ancient universe, to look at something 1,300 light years away, a stellar nursery where stars are forming right now, in the present, from the same kinds of gas clouds that produced the first galaxies. And what Webb found there was both beautiful and strange in a completely different way from everything that came before. In the Orion Nebula's dense, chaotic interior, Webb identified a population of small, faint objects that had not been clearly seen before. Planet-sized objects, roughly the mass of Jupiter or somewhat larger, drifting freely through the nebula, with bound to any parent star, not planets orbiting a sun. Rogue worlds wandering through the stellar nursery in pairs, two objects orbiting each other in the open space of the nebula without any stellar anchor. Researchers called them Jupiter mass binary objects, and their existence suggests something unexpected. Planet-sized objects can apparently form independently, not as byproducts of star formation in a protoplanetary disk, but spontaneously, from the same chaotic fragmentation process that produces stars. The nebula is making worlds on its own. Beyond the nebula, Webb began delivering on one of its most anticipated capabilities, the direct chemical analysis of exoplanet atmospheres. When a planet passes in front of its host star, a thin sliver of starlight filters through the planet's atmosphere. Different molecules absorb different wavelengths. Webb's spectrographs can read those absorptions with a precision no previous instrument approached, identifying the chemical fingerprints of whatever the atmosphere contains. In 2022, Webb confirmed the presence of carbon dioxide in the atmosphere of WASP 39b, a gas giant orbiting a star 700 light-years away. This was the first unambiguous detection of carbon dioxide in an exoplanet atmosphere. Carbon dioxide is a molecule produced on Earth by geological and biological processes alike. Finding it elsewhere does not mean life, but it demonstrates that Webb can read atmospheric chemistry from hundreds of light-years away with enough clarity to identify specific molecules. What is confirmed is the capability and the detections themselves. Carbon dioxide on WASP 39b is established science. The rogue planet pairs in Orion are established observations. What remains unknown is what these findings tell us about the prevalence of complex atmospheric chemistry and planet formation across the universe at large. Here is why this chapter belongs in a video about cosmological anomalies. Everything Webb has found about the early universe, the faster structure formation, the more efficient star making, the unusual stellar populations, if those processes operated throughout cosmic history in ways our models underestimate, they also operated in the formation of planetary systems. A universe that makes galaxies and black holes faster and more efficiently than we assumed also makes planets faster and more efficiently. The cosmic anomalies and the planetary detections are not separate stories. They are told by the same physics, operating at different scales. And the scale question runs in the other direction too, because the most unsettling possibility raised by Webb's cosmological anomalies is not about galaxies or black holes, but about something more fundamental than either. The possibility that the numbers governing all of physics have not always been what they are today. This chapter moves from what the universe contains to how it operates, and it asks a question that sounds almost philosophical, but is being tested right now with real instruments and real data. Modern physics rests on a set of numbers that appear to be absolutely fixed. The speed of light in a vacuum, the gravitational constant, the charge of an electron, the ratio of a proton's mass to an electron's mass, the fine structure constant, which governs the strength of the electromagnetic force and determines how atoms absorb and emit light. These numbers are called the fundamental constants of nature, and every equation in physics depends on them. They are assumed to be the same everywhere in the universe, and at every moment in cosmic history, they are, by definition, constant. But that assumption has never been rigorously tested across the full span of cosmic time. It has been assumed because the alternative is extremely uncomfortable, and because until recently, no instrument existed with the precision to detect small variations, even if they existed. Webb exists, and its spectroscopic capability is now being used to test whether the fine structure constant has always had the value it has today. Here is how the test works. When atoms absorb or emit light, they do so at specific, precise wavelengths determined by the fine structure constant. These wavelengths are known with extraordinary precision from laboratory measurements. When Webb observes a distant galaxy and captures the light from its gas, that light carries the absorption fingerprints of atoms in the galaxy's atmosphere. If the fine structure constant had even a slightly different value when that light was emitted, the absorption lines will be shifted by a tiny amount relative to what laboratory physics predicts. By comparing the observed wavelengths to laboratory values across many atomic transitions in many distant galaxies, researchers can test whether the constant varied. Previous studies using ground-based telescopes produced hints. Analyses of quasar spectra in the early 2000s suggested a possible spatial variation in the fine structure constant, slightly smaller in one direction across the sky, slightly larger in the opposite direction. The variation was tiny, well below 1%, but it was directional, which is precisely what you would not expect from a truly universal constant. What is confirmed is that Webb's spectroscopic precision is sufficient to test these earlier hints at substantially higher sensitivity. Results from this ongoing program are still being analyzed and have not yet produced a confirmed detection of variation. What is unknown is whether a real variation exists at a level Webb can detect. If it does, it has not yet been definitively identified in published results. Here is why this matters beyond technical curiosity. If the fine structure constant, or any other fundamental constant, had a different value in the early universe, then the physics of the early universe was genuinely different. Not just the conditions, not just the temperature or density, but the underlying rules. Atoms would have behaved differently. Cooling processes would have operated differently. Star formation thresholds would have been different. Every one of Webb's anomalies, the impossible galaxies, the early spirals, the chemical enrichment puzzle, could potentially be explained in a single stroke if the constants governing atomic physics were slightly different in the first billion years of cosmic history. The implications for our self-understanding are staggering. The laws of physics, as we know them, would not be eternal laws in the fullest sense. They would be the current values of parameters that evolved over cosmic time, like the temperature of a cooling object, constants that are not constant, laws that are not universal. These are ideas that serious physicists are publishing in serious journals. They remain unconfirmed, but the fact that we now have an instrument capable of testing them meaningfully is itself a landmark moment. If the constants might be changing, the next question almost asks itself: what about the force that dominates the universe's energy budget? The one that makes up 68% of everything that exists? The one whose nature has been unknown since the day it was discovered? Dark energy was found in 1998 when two independent teams measuring the expansion rate of the universe discovered that distant supernovae were dimmer than expected. Not slightly dimmer, dimmer in a way that implied they were farther away than a decelerating or even a steadily expanding universe would place them. The universe was not just expanding, it was accelerating. Something was pushing space apart with increasing force. That something was named dark energy. In the standard model, dark energy is described as the cosmological constant, a fixed energy density built into the fabric of space itself. It has one value, everywhere, always. This description fits decades of available data, but it has always carried a theoretical catastrophe. When physicists calculate what the cosmological constant's value should be from quantum field theory, the predicted value is roughly 120 orders of magnitude larger than what is actually observed. Something is cancelling out almost all of the predicted energy with extraordinary precision. We do not know what. This is called the vacuum catastrophe, and it is the largest discrepancy between theory and observation in the history of science. Webb, combined with data from large ground-based galaxy surveys, is now providing the first observational hints that dark energy may not be constant after all. In 2024, results from the Dark Energy Spectroscopic Instrument Survey, combined with Webb observations of high redshift supernovae, produced a dataset that, when analyzed, favored cosmological models in which dark energy's strength varies over time rather than remaining fixed. The signal is not yet at the level of a confirmed detection. Researchers describe it carefully as a hint, a preference in the data, rather than a definitive measurement. But it is present in multiple independent analyses of the combined dataset. If dark energy is not constant, it has a name in theoretical physics: quintessence, a dynamical field that evolves over cosmic time like other fields in physics, changing its energy density as the universe expands. Quintessence models have been developed for decades, but have always lacked observational support. Webb may be providing the first real signal. What is confirmed is that the combined dataset shows a statistical preference for evolving dark energy over a strict cosmological constant. What is not confirmed is whether this preference will survive as more data is collected, or whether it will diminish as measurement precision improves. The current signal is real but not yet definitive. Here is what a changing dark energy would mean. If dark energy was stronger in the past than it is today, it would have expanded the universe more rapidly in earlier epochs than the standard model assumes. That additional early expansion would leave a fingerprint on the Hubble constant measurement derived from the cosmic microwave background, potentially contributing to the Hubble tension. The same physics that alters dark energy's behavior could simultaneously explain why the two Hubble constant measurements disagree, one anomaly explaining another. The threads pulling tighter. Science is often described as a self-correcting process. Data arrives, models are tested, the wrong ones are discarded, the right ones survive. This description is accurate but incomplete, because science is done by people, and people have careers and identities and decades of accumulated work built on specific frameworks. When those frameworks come under pressure, the correction process is not painless. Inside the community of cosmologists and observational astronomers, Webb's findings have produced something that does not have a clean name in scientific literature. A reckoning is perhaps the right word. Senior researchers, people who built the standard model piece by piece, over 30 and 40-year careers, are confronting data that their own framework did not predict and does not easily explain. This is confirmed. Multiple leading cosmologists have publicly acknowledged that the lambda CDM model is under serious pressure. At major conferences since 2022, sessions on the Hubble tension and on early galaxy anomalies have drawn standing room crowds and produced debates of an intensity that the field had not seen in years. The disagreements are sometimes sharp, not personal but pointed. Arguments about statistical methodology, about how galaxy masses should be estimated, about whether specific Webb detections have been interpreted correctly. These are the arguments of people who care deeply about getting the answer right, and who disagree, sometimes vigorously, about what getting it right requires. For researchers who spent their most productive years developing the simulations, the theoretical frameworks, and the observational programs that the standard model is built on, the experience carries a specific weight. One senior cosmologist, speaking at a symposium in late 2023, described the situation in terms that were unusually candid for a scientific setting. She said that spending 3 decades building a model that matches 9/10 of what you observe, and then watching one telescope find the 10th that does not match, feels less like a setback and more like the end of a conversation you are not ready to stop having. That is not weakness. That is the authentic experience of science at its most human. The model was not wrong in trivial ways. It was right in extraordinary, precise, beautiful ways across an enormous range of observations. The fact that it is now under pressure at its edges does not erase the achievement. It opens the next chapter of it. What is genuinely difficult is the practical dimension. Research programs built on standard model predictions are being re-evaluated. Grant proposals that assumed the framework was essentially complete are being rewritten. Collaborations formed around specific theoretical predictions are now uncertain about what to predict. The machinery of science, the funding cycles, the publication landscape, the conference priorities, is in the process of recalibrating around a new set of open questions. That recalibration is not instantaneous. It is disruptive in ways that rarely make it into scientific papers, but that shape the lived experience of researchers every day. And for the people most invested in the model, the most senior, the most decorated, the ones whose names appear on the foundational papers, Webb has delivered a particular kind of challenge. Not the challenge of being proven wrong, which would at least have the clarity of a definitive answer. The challenge of being proven incomplete, which is more ambiguous, more prolonged, and in some ways harder to navigate. In 1983, a physicist named Mordechai Milgrom proposed that at very low accelerations, specifically the kind experienced by stars at the outer edges of galaxies, Newtonian gravity does not quite apply. He proposed that below a certain acceleration threshold, gravity becomes slightly stronger than Newton's equations predict. He called it modified Newtonian dynamics. The mainstream largely ignored it. Dark matter had too much evidence in its favor. The cosmic microwave background matched dark matter models. The large-scale cosmic web matched dark matter simulations. Cluster dynamics required dark matter. MUND struggled at every scale above individual galaxies. For decades, it existed at the margins of the field, developed by a small dedicated community, but treated with skepticism by most. Webb has not confirmed MOND. What it has done is narrow the gap between MOND's predictions and specific observations in ways that have brought new attention to modified gravity frameworks from researchers who previously ignored them. What is confirmed is that in at least some of Webb's observations of small, isolated early galaxies, modified gravity frameworks produce rotation profiles that match the data as well as or slightly better than standard dark matter simulations. What is not confirmed is whether this represents a genuine signal or a coincidence of the specific observational conditions of those particular objects. The broader observational challenges for MOND at cluster scales and cosmic web scales remain unresolved. The field is not converting to modified gravity, but it is listening to it in ways it was not before Webb launched, and that shift in attention reflects something important. When a model is under pressure from multiple directions simultaneously, ideas that were previously dismissed as unable to replace it start to be re-examined for whether they might contribute partial solutions, even if they cannot provide complete ones. This chapter goes to the deepest foundation of all, not a specific observation, not a specific tension, the assumption that makes all the equations solvable in the first place. The cosmological principle states that the universe, on large enough scales, looks the same in every direction and from every location. No preferred places, no preferred directions, no special axes. A universe that is homogeneous and isotropic at the scale of hundreds of millions of light years and above. This is not just a philosophical preference. Without it, the equations governing cosmic evolution become unsolvable. It is built into the mathematical foundations of modern cosmology. The challenge to this principle did not begin with Webb. The Hercules Corona Borealis Great Wall, a concentration of galaxies stretching roughly 10 billion light-years across, was identified before Webb launched. Our models put an upper limit on structures gravity can build within the age of the universe at roughly 1.2 billion light-years. The Great Wall is nearly 10 times that size. Its existence has been debated, with some researchers questioning the detection methodology and others arguing it represents a genuine violation of the cosmological principle. What Webb has added is a statistical layer. In multiple deep field observations, Webb finds galaxy phi distributions and alignment patterns that appear non-random at scales that should, according to the cosmological principle, be smooth. These are not yet confirmed violations. They are flagged statistical anomalies, present in the data, being investigated, not yet elevated to the status of definitive detections of inhomogeneity. What is confirmed is that the question is now being asked more seriously than before. What is unknown is whether the apparent non-randomness in Webb's data and in structures like the Great Wall represents a genuine failure of the cosmological principle, an observational bias from our limited vantage point, or a statistical artifact of how large datasets are analyzed. The debate is ongoing and genuinely unresolved. This is the chapter where individual threads become a single question. We have covered the Hubble tension, the impossible galaxies, the dead galaxies, the mass excess, the early spirals, the supermassive black holes, the protocluster development, the cosmic microwave background anomalies, the elevated ultraviolet output, the population 3 enrichment puzzle, the possible variation in constants, and the hints of evolving dark energy, each one addressed by its own researchers with its own data and its own proposed solutions. But what if they are not separate problems? What if they are different faces of a single underlying reality? Here is the possibility that a growing number of theorists are beginning to write about with careful, measured language in peer-reviewed papers. The early universe may have operated under conditions, and perhaps under physics, that were not identical to what governs the universe today. Consider what that single statement would explain. If the fundamental constants, including those governing atomic cooling and star formation, were slightly different in the first billion years, early galaxies would form stars more efficiently. The mass excess is explained. If dark energy was stronger in the early universe, the Hubble constant derived from the cosmic microwave background would be biased, producing the tension. If inflation produced non-standard initial conditions with subtle large-scale structure, it would explain both the cosmic microwave background anomalies and the overdeveloped protoclusters Webb is finding, as both would reflect the same primordial pattern in the density field. And if any of these early universe modifications also affected how dark matter clustered and how halos formed, the scaffolding problem and the early black hole mass problem both become more tractable. 4 separate anomalies, one underlying cause, a universe whose early chapter operated by rules that have since evolved into the ones we study in laboratories today. This is not confirmed. It is a theoretical possibility that the data is consistent with, not a demonstrated fact. But what makes it worth taking seriously is that it connects anomalies from completely independent observational programs, measured by completely independent teams using completely independent techniques, all pointing in the same direction. The early universe was more productive, more efficient, more organized, and more energetic than our model of it predicts. The universe does not owe us an explanation that fits our current framework. It owes us nothing. We owe it honesty about what we are finding. There is a second human story inside this scientific moment, and it belongs to a different generation. Graduate students and postdoctoral researchers entering cosmology in the early 2020s were told, not incorrectly, that they were entering a mature field. The foundational questions had been answered. The parameters had been measured. The work remaining was precision and detail. They trained on the standard model, built their dissertations around its predictions, developed their early careers on its framework. Then Webb launched, and the field they had trained for turned out to be not a finishing project, but an opening one. For some, this has been genuinely energizing. Several early career researchers have described in interviews the unusual experience of watching a decades-old consensus develop real cracks and feeling the space open up for genuinely new ideas. One postdoctoral fellow at a major research university described it as feeling like arriving at a library that you expected to be mostly full and finding entire wings with empty shelves. The emptiness is not a failure, it is an invitation. For others, the uncertainty is harder to navigate. Research careers are built on publications, and publications require productive lines of inquiry. When the theoretical framework that defines which questions are worth asking is under pressure, identifying the right questions to pursue becomes significantly harder. Funding follows established frameworks. Grant reviewers evaluate proposals against known standards. A proposal to explore genuinely heterodox ideas in a field experiencing paradigm pressure may be evaluated by reviewers who are themselves uncertain about which direction the field is moving. What is confirmed is that the early career researchers now working on Webb data are doing science at a genuinely unusual moment. The questions are open in ways they were not expected to be. What is unknown, for these researchers personally, is which of the competing frameworks being developed will eventually prevail, and whose career trajectory will be shaped by having been on the right side of that theoretical competition. Both the senior researchers from the previous human element chapter and these early career ones share something important. They are all doing their work in real time, without the benefit of hindsight, without knowing how the story ends. That is the condition of science at any genuinely productive moment. The uncertainty is not a flaw in the process. It is the process. Reset the scale completely. Forget individual galaxies for a moment. Forget even galaxy clusters. Go to the largest single structure ever identified in the observable universe. The Hercules Corona Borealis Great Wall spans approximately 10 billion light-years. Let that number sit. The observable universe is roughly 93 billion light-years across. A single structure, a concentration of galaxy clusters and superclusters connected across a vast region of space. occupies more than a tenth of the entire observable cosmos. It is not a wall in any literal sense. It is a vast overdensity, a region where the universe's matter is significantly more concentrated than the surrounding average, but its scale defies every simulation ever run on any supercomputer using the standard model's physics. Gravity cannot build structures larger than a certain size within the age of the universe. The speed of light limits how quickly gravitational influence can travel, setting a ceiling on the scale of structures that can be causally connected and therefore gravitationally organized. That ceiling, roughly 1.2 billion light-years under standard physics, is not even close to 10 billion. The Great Wall, if real as characterized, is not a large structure. It is an impossibly large one, larger than causal physics should allow. The detection remains debated. Some researchers argue it reflects a statistical artifact in how gamma-ray burst distributions are used to map large-scale structure. Others argue the detection methodology is sound and the structure is real. Webb is not resolving this debate directly, but by adding data on galaxy distributions at high redshift that show their own signs of large-scale non-uniformity, Webb is keeping the question alive at a time when the field might otherwise have allowed it to fade. If structures at this scale are real, the cosmological principle fails. And if the cosmological principle fails, the entire mathematical foundation of modern cosmology needs to be rebuilt on different assumptions. This is not the consensus view, but it is the view that the data, at its most uncomfortable reading, points toward. The standard model is under pressure. The replacement has not arrived. Instead, 4 serious theoretical frameworks are competing to explain what Webb has found, each requiring the field to give up something different. The first is non-standard inflation. This keeps most of the standard model intact, but modifies the inflationary period to produce non-Gaussian initial fluctuations, meaning the seeds of structure were distributed in ways that allowed faster growth in the early universe. This is the most conservative option. It requires the least departure from established physics and is compatible with most existing observations. The second is early dark energy, a brief burst of additional dark energy in the first few 100,000 years of cosmic history temporarily accelerated the early expansion, leaving a fingerprint in the Hubble constant discrepancy. Several research groups have developed detailed models and are testing them against Webb data. They work partially. None yet reproduces all observed features simultaneously without introducing new problems elsewhere. The third is interacting dark matter. Standard dark matter interacts with ordinary matter only through gravity. What if dark matter particles also interact weakly with each other or with radiation in ways current models ignore? Self-interactions could change how halos form, allowing faster galaxy growth in the early universe and potentially explaining the mass anomalies Webb keeps finding. This framework has gained significant theoretical attention since Webb launched. The fourth is evolving dark energy, the quintessence scenario described earlier in this video. If dark energy's strength has changed over cosmic time, the universe's expansion history is different from what the standard model assumes, with implications for every distance measurement and age estimate in cosmology. None of these frameworks is complete. None resolves all of Webb's anomalies simultaneously. The field is in productive theoretical competition, which is exactly the state that precedes major advances. What all 4 share is a recognition that the standard model is missing something, and that something operated throughout the early universe in ways that left detectable signatures in the data Webb is now producing. Science answers questions by building better instruments, and the specific questions Webb has raised are now shaping the design priorities of the next generation of observatories. The extremely large telescope, currently under construction on Cerro Armazones in Chile's Atacama Desert, will have a primary mirror nearly 40 meters across, making it the largest optical and near-infrared telescope ever built. When it begins science operations in the late 2020s, it will be capable of directly imaging rocky planets orbiting nearby stars and analyzing their atmospheres at sensitivity levels that Webb cannot achieve for most targets. For cosmology, its spectroscopic capability will allow it to measure the Hubble constant through independent methods and to analyze early galaxy chemistry with a precision that can distinguish between the competing theoretical frameworks described in the previous chapter. The Nancy Grace Roman Space Telescope, a NASA mission scheduled to launch in the late 2020s, will observe fields of view roughly 100 times larger than Webb per image. Where Webb goes deep and narrow, Roman goes wide and fast. This is precisely what is needed to build the large statistical samples required to test the mass anomaly problem definitively, to map the large-scale structure of the early universe in enough volume to test the cosmological principle, and to conduct a supernovae survey large enough to measure the Hubble constant and the evolution of dark energy with substantially improved precision. CMB Stage 4, a ground-based array of microwave telescopes planned for deployment at the South Pole and in Chile, will map the cosmic microwave background with a precision roughly 10 times better than the Planck satellite achieved. If the Hubble tension is a genuine discrepancy in early universe physics, CMBS4 should definitively confirm it and narrow down which theoretical explanations are viable. It will also search for the gravitational wave signature of inflation, which would provide direct information about the conditions that set the universe's initial state. A fourth project, still in planning stages at multiple space agencies, involves a large space-based infrared observatory designed specifically to push beyond Webb's reach into the universe's first 200 million years, targeting the transition from the cosmic dark ages to the first light. If population 3 stars exist in detectable numbers, this observatory would find them, directly confirming or refuting the theoretical picture of the first stellar generation that underlies so many of Webb's anomalies. What is confirmed is that all 3 primary projects are funded, in construction or in advanced development, and on track to deliver data within the next decade. What is unknown is what that data will show. It will either confirm one of the competing frameworks being developed to explain Webb's anomalies, or it will produce new anomalies that none of those frameworks anticipated. Both outcomes are valuable. Both move the story forward. Both are, in their own way, a form of success for the scientific enterprise. Because the goal was never to confirm what we already knew. The goal was always to find out what is actually true. We began this video with a number on a whiteboard. The Hubble constant, a measurement so fundamental that getting it right was supposed to be one of the finishing tasks of modern cosmology. 2 groups of scientists measured it with extraordinary care and got different answers. Webb was built to settle it. It did not settle it. It confirmed that both answers are real, that the gap between them is real, and that something in our picture of the universe is missing. That number is still on the whiteboard. It has not been erased. What has changed is what surrounds it. A field's worth of additional anomalies, each one independently established, each one pointing in the same direction. The early universe was more productive, more structured, more organized, and more energetic than the model built to describe it. Galaxies that should not have existed were there. Black holes that should not have grown were massive. Structures that should not have organized were already organizing. Light that should not have been so bright was blazing. The James Webb Space Telescope did not break cosmology. It found the specific places where our picture of the cosmos was thinner than we knew, and it found them not by looking for trouble, but simply by looking more clearly than anything that came before it. What does it mean to live in a universe that keeps refusing to be fully understood? It means, first, that the universe is not obligated to be simple. For decades, the convergence of cosmological measurements on a clean, elegant standard model felt like a destination. The lambda CDM model worked. Its parameters were measured. The picture seemed nearly complete. The universe was under no obligation to remain within the boundaries of that elegance, and Webb has demonstrated, with extraordinary clarity, that it has not. It means, second, that science is working exactly as it should. The whole point of building instruments with greater precision is to find the places where current understanding fails. Webb is doing precisely what it was built to do. The anomalies it is finding are not a failure of the telescope or the researchers who built it. They are the telescope succeeding. They are science functioning at its highest purpose, finding the honest edges of what we know. It means, third, that we are at a genuinely rare moment. The moments when major scientific frameworks develop real cracks and new ones begin to form are not common. They happen a handful of times per century in any given field. We are inside one of those moments right now, watching it unfold in real time through the data Webb continues to send back from its position 1,000,000 miles from Earth. Every week, new observations. Every month, new papers. Every year, the picture sharpens in ways that make the questions more specific, more testable, more answerable by the next generation of instruments being built in Chilean deserts and at the South Pole and in spacecraft assembly facilities right now. And it means, finally, something that is harder to quantify but no less real. The universe has never, in the entire history of human inquiry, turned out to be smaller than we thought. Every expansion of our instruments has revealed more. Every increase in precision has uncovered new structure. Every answer has opened a deeper door. The universe Webb is revealing is not less beautiful than the one the standard model described. It is more beautiful because it is more surprising, because it is more resistant to the comfortable story we had assembled for it. Beauty in science does not require simplicity. It requires honesty, and Webb is enforcing honesty about what we know and what we do not, at a precision and a depth no instrument before it could achieve. A telescope 1,000,000 miles from Earth is still out there right now, collecting ancient light. Light from the edge of what we can see. Light that has been traveling since before our planet, our star, or the raw material that would build them had yet formed. And in that light, across billions of years of cosmic distance, the universe is still speaking, still telling us things we did not expect to hear, still turning out to be stranger, larger, and more intricate than any model we have yet built for it. That is not a problem to be solved. That is the point of the whole endeavor.